Today I discuss one important topics related to linear transformation. Okay, we also start from one theorem related to that. We first discuss so many theorems and definitions and examples related to this theorem. Today we also give one important theorem. We write it now. Okay, with that first statement of this theorem. Let V and W be vector spaces over a field F. Okay, over a field F, and suppose that V1, V2, Vn is a basis for V. Is a basis for V for W1, W2, Wn in W. Okay, there exists exactly one linear transformations okay, tv2w such that t of vi equal to wi for I equal to 1 2 n. Okay, this one is an important theorem. This one v1 v2 vn is basis and w1 w2 wn in w, then there exists exactly one linear transformation satisfies tvi equal to wi. Okay, so we're now going to proof of that. We write here proof and going to further discussion of that. So let x belongs to v. Okay, let x belongs to v, then what happened, x equal to here I equal to 1 to n. Okay, ai vi, where a1 a2 an are unique scalar, where a1 a2 an are unique scalars. Now define t v2w. Okay, by here tx equal to, okay, I equal to 1 to n aiwi. Okay, then what we have to prove, we'll just write this one, define t. Now we're going to prove that first t be linear. Okay, first we write t be linear. Okay, then suppose that uv belongs to v. Okay, and d belongs to f, and t belongs to this f. Then we may write, okay, then we may write here u equal to summation I equal to 1 to n pi vi, and v equal to summation I equal to 1 to n ci vi. Okay, for some scalar Also write it in above. We erase that portion. Okay, we write it in this way. This one, that means for some scalar, for some scalars v1 v2 vn, and here c1 c2 cn. Thus what happened here? Thus du plus v equal to, we write it in this way, summation I equal to 1 to n dvi plus ci. Okay, here vi. So what happened? So we write it in this way, t of du plus v equal to summation I equal to 1 to n, okay, dvi plus ci, here t of vi, okay, that means wy. We write it in this way, I equal to 1 to n dvi plus ci, here wy, okay. Then this one equal to d summation I equal to 1 to n diwy plus summation I equal to 1 to n ciwy equal to d of du, okay, plus dv. Understood? Then what happened? Then we also, that means write it in this way, t of du plus v equal to d of du plus dv. Hence t is linear. Hence dv linear. Okay. Now we erase that portion and going to proof of that. Okay. dv unique. We erase that whole portion and going to proof of that dv unique. Okay. Here we write in this way. Okay. That means we also, that means option we also write clearly. Clearly what? Clearly t of vi equal to wi. Okay. For I equal to 1 2 dot n. Okay. Now we write the option B in this one and C. T is unique. T is unique. Then what happened? Okay. We write it in this way. Suppose that okay, u v to w, okay, is linear, and u of vi equal to wi for I equal to 1 to dot n. Then for x belongs to v, then for x belongs to v with x equal to its linear combinations of vi, okay, I equal to 1 to n. We have what? We have ux equal to, here we write in this way, that means u of I equal to 1 to n aivi equal to what? Equal to, in this way we write I equal to 1 to n ai u of vi equal to what? Equal to, write in this way, I equal to 1 to n ai wi equal to what? Equal to t of x. Okay, so we also write in this way. That means if u of vi equal to wi, then obviously u equal to t. Okay, u equal to t. Understood? Then we also prove this one. That means we get exactly one linear transformation. This satisfies that tv to w tvi equal to wi. Understood? Then we also going to discussion one corollary related to that theorem. Okay, we write it in lower portion. Okay, we write it this corollary. What this corollary tells us. Okay, we write it in this way. Let v and w be vector space. Let v and w be vector spaces, and and suppose that v has a finite basis. Okay, v has a finite basis v1 v2 vn. Understood? And if ut here v2w ut v2w ut v2w are linear and u of vi equal to t of vi. Okay, for I equal to 1 to n. Understood? We erase our portion and going to further discussion of that. For I equal to 1 to n. Okay, then what happened? Then u equal to t. Okay, let v and w be vector spaces, and suppose that v has a finite basis v1 v2 vn. If ut v2w are linear and uvi equal to tvi for I equal to 1 to n, then u equal to t. Understood? Now we also, that means, give some example related to that topics. Okay, we erase that portion and going to further discussion of that. We write it in the example here. Okay, we write it example here. Let t r square, let t r square to r square, okay, be the linear transformation, be the linear transformation, okay, defined by what? T of a1 a2 equal to, we write it in this way, 2a2 difference a1 and here 3a1. Okay, and suppose that okay, u r square to r square, okay, u r square to r square be linear, okay, And obviously if you know that, that means if we know that what u of 1 2 equal to here 3 3 and u of 1 1 equal to 1 3. Okay, then what happened? Then u equal to t. Understood why this one is happen? That means okay, obviously we write it in this way. That means this 1 2 and 1 1. Okay, be a basis for r square. Okay, and we also see that how this one is, that means happen. Okay, this one if this one is basis, and obviously t of u vi equal to ui. Okay, and u of vi equal to wi, t of vi equal to wi, and t of vi we also check it now here. That means t of 1 2 equal to what? T of 1 2 equal to here 4 difference 1 and here 3. Okay, so 3 3 equal to u of 1 2, and in this way t of 1 1 equal to what? T of 1 1 equal to 2 difference 1 and 3. That means 1 3 equal to u of 1 1. Understood? Then what happened? That means this one are basis for r square, and obviously satisfies t of t of vi equal to u of vi. Okay, in this way. And so we also talk about that u equal to t. That means consequent example or related example of this theorem we also give here. Okay, now we going to discussion, that means another topics here. We also known about that left shift operator and right shift operator. We just discuss this one now. We erase that portion and going to further discussion of that. Okay, so we write it in this way: left shift operator, okay, and right shift operator, and right shift operator. Okay, so we write it in this way: left shift operator and right shift operator. Okay, let V be a vector space. Let V be a vector space. Okay, of sequences. Vector space of sequences, and obviously described. That means also known about these sequences. Okay, that means also known about a1 a2 an in this way. Okay, so this one is in this type of sequence. So we write it here: v is the vector space of sequences. This one a1 an, okay, where n belongs to natural number. And then what happened? Then we're also going to define the function. Define the function t u here v to v by. Okay, t of a1 a2 dot equal to what? Equal to a2 a3 dot. Okay, and u of a1 a2 dot equal to what? 0 a1 a2 dot dot dot. Okay, in this way we also write this one. Then what t are t be a left shift operator. Okay, t be a left shift operator on v, and u be a right shift operator on v. Understood? We also know about that this one, this following properties satisfies by this left shift and right shift operator. We write it in star and mark it tu be linear. Okay, linear, and obviously we also write it in this way: t is on 2 but not on 1, t is on 2 but not 1 1 1 to 1. Okay, and here we also write what that means: u is 1 to 1, u is 1 to 1 but not 1 to. Okay, understood? Here tu linear and t on 2 but not 1 to 1, u is 1 to 1 but not on 2. Understood? This one is too easy. We now today we not discuss this one. Okay, u is 1 1, we also discuss this it so surely, but not on 2. Okay, why not on 2? Because if we write here, that means here kernel of u is not 0. Okay, have dimension 1, and in this way t is on 2. That means every image have some pre-image, but we also not talk about that. This one is 1 to 1. Okay, because if a1 is different then images are same, so we not talk about this one. It's 1 1. Okay, so well, also it is that portion and going to further discussion of that. Okay, now let's talk about projection of some space along another space. So we erase that portion and going to further discussion of that. We write it here, definition. Okay, definition in this way. How let V be a vector space, let V be a vector space. Okay, and W1 and W2 and W1 and W2. Okay, be subspaces of V, be subspaces of V, and such that, okay, such that V equal to W1 plus direct sum of W2. Okay, then what happened? We also talk about that. Okay, a function t v to v is called the projection, is called the projection on W1, okay, along W2, if what, if for x equal to x1 plus x2, okay, with x1 belongs to W1 and x2 belongs to W2. Okay, and we have what we have what tx equal to x1. Understood? Then we call it projection of w1 along w2, and obviously we call it in this way. That means if we call it u, okay, if we call it u, here v to v is called the projection. It's called the projection on w2 along w1 if what if for x equal to x1 plus x2 with x1 belongs to w1 and x2 belongs to w2, we have what we have t of x equal to x2. Understood? So we write it in this way: t of x equal to x1 and t of x equal to x2. Okay, here in this way we write t of x1 plus x2 equal to x1, and here in this way we write t of x1 plus x2 equal to x2. Okay, let V be vector space and W1 W2 be subspace of V such that V equal to W1 direct sum W2. A function T V to V is called the projection on W1, okay, along W2 if this one is satisfied. Tx equal to x1, tx1 plus x2 equal to x1, okay, and u v to v is called the projection on W2 along w1. Projection on w2 along w1, we call it in this way. What that means, sorry, here not t, oh, we do it wrong. ux equal to x2 and ux1 plus x2 equal to x2. Understood? So in this way we also discuss projection of any subspace along another subspace. Okay, so we also understood that problem too easily. We write it in this definition. Okay, then we also going to definition of another T-invariant subspace. We erase that portion and going to further discussion of that. Okay, okay, here we write T-invariant. Okay, we write definition. Let V be a vector space. Let V be a vector space. Okay, and let T V to V, okay, be linear. V to V be linear, and a subspace W of V, a subspace W of V is said to be what? T-invariant. Okay, if Tx belongs to W, if Tx belongs to W for every x belongs to W, okay, and that is what? That is TW subset of W. Okay, what happen if w is T invariant. Okay, if w is T invariant, then what happen? Then we define the restriction of T. We define the restriction of T on W. Okay, we define the restriction of T on W to be the function TW, here W to W. Okay, defined by 2wx equal to tx. Okay, for all x belongs to W. Then if W is T invariant, okay, W is T invariant, that means subspace is T invariant. Here a subspace W of V is T invariant, then this one happened, TW subset of W. Okay, and here W is T invariant, and we define the restriction of T on W to be the function TW equal to Tx for all x belongs to W. Understood? Not a problem at all. So we also going to some discussion of that, the subspace example, the subspace. Okay, the subspaces 0, okay, V, RT and NT and NT are all T invariant. Okay, sorry, T invariant here, that means invariant. Okay, all are A. Then T invariant, that means one subspace T invariant means T of W subset of W, that means T of X belongs to W. Okay, and again if T with W belongs to T invariant, then restriction of T on W to be the function TWX equal to TX. Then the subspaces 0, V, RT, NT are all T invariant. That means range of T, null space of T and 0 and obviously whole space P are all T invariant. Okay, so in this way we also discussion T invariant subspaces. Okay, and today we not discuss more, so today we stop here. If you get this type of videos, please subscribe my channel, and if you want to give like, please click on like options, and if you have any questions, comments, suggestions, write it in comment box. So today I stop here. Thank you. Follow my channel and subscribe my channel.